Okay, thank you so much. And first of all, I'd like to thank Christina and Kyung for inviting me over here, also for the very kind introduction. This is my first international travel since the pandemic started. So I've been so excited and looking forward to this event as well. And never mentioned about the event is in such a beautiful and historical city. I'm Helen Li from Duke University. I've been working on neuromorphic computing and machine learning acceleration. So today I'm going to talk about our work related to efficient machine learning, particularly focusing on the algorithm and hardware co-design side. Okay, I guess we don't have to mention more about how important of machine learning, how popular this area, and how many works people have been done on deep learnings and deep neural networks and so on and so forth. So people tend to explore the usage of DNNs in many applications and domains, and the interest is still growing up. Well, even we're talking about this, and as people working on hardware and systems, and we can clearly say there's a huge problem. The problem is rooted from the software designs. In fact, the current approach trying to obtain higher prediction accuracy by sacrificing or ignoring the growth of the algorithm side. So here I give two examples. One example is on the image classification on ImageNet and data set. So the figure on the left-hand side, if you take a look, each node represents a model, and the area, the size of the circle indicating the model size measured by the number of the parameters. Well, x-axis is indication the computation cost measured by operation like gigaops, and y-axis is corresponding to the top one accuracy on ImageNet. So as you can see, general trend when the accuracy improves, and it must associate with the increase of the models, and therefore the increase of the computation cost. And this trend is particularly obvious if you're looking at the series model. For example, if you're looking at the ResNet, starting from ResNet 18 to 31, 34, 50, 101, and 154, right? The similar trend actually can be obtained when we're looking at the language modelings on the right-hand side. So this is only for the transformer model. Y-axis represent the test perplexity, the lower the better. And the trend is also very obvious, like the prediction accuracy improvement is gained based on the model size increase. Well, this is from algorithm or the software side, why this is a big threat or challenge to the hardware designs. First of all, as you can see, when we have larger models, training becomes extremely difficult. It takes longer time, indicating longer research and production cycles. We're also talking about the sustainabilities. Obviously, large model training consumes more energies, and this is definitely will be an issue. On the deployment side, well, when we apply those big models on, for example, edge device, many edge devices is constrained with computation resources, memory resources, or even communication resources. So a lot of times, those edge devices has to sacrifice the accuracy and live with the low accuracy model. Well, even the large devices can accommodate with those large models, it's still indicating the operation time is longer. So people have been working on hardware designs and trying to accommodate the requirement from algorithm side. I don't have to mention how much efforts, because I think everyone here has been done tremendous research works in this field. But one thing I wanted to mention is there's a huge mismatch between the algorithms and hardware designs. Generally speaking, hardware is more rigid, especially once we haven't made the hardware fabricate. And then, on the other hand, the algorithm side has more flexibilities. So it's generally the question is, at the different design cycles, can we accommodate the situation? For example, before hardware is made, can we try to improve the architectures and the systems, right, to offer better optimization? Well, on the other hand, once hardware is there, how to optimize the algorithms so it can perform better on the hardware. And this is essentially the core of today's talk. So I will start with the cross-layer co-design for high efficiency. And on this part, I will give two examples. One example is talking about for the given hardware, how can we have some higher level abstract and implant this to the DNN model trainings, made it perform better on the given hardware platform. Another example is, again, with the given accelerator designs and DNN models, is there any things we can do so the deployment itself becomes more efficient? Well, afterwards, I will going to briefly touch about the neural architecture search, which is a part of the auto machine learning approach in recent days. I know Diana, the TPC chair, she has been working in this field. Unfortunately, she couldn't make today's meetings, but we share the common interest and interested in how to automate the machine learning designs and trying to have a better sustainability. At the end, I will conclude today's talk. All right, so I will start with the cross-layer design for high efficiency. Previous slides, I mentioned about the huge model size. In fact, there is another observation, is that most of the DNN models are quite sparse and redundant. So in other words, if we are able to remove those redundancies, we can reduce the computation, storage, communication cost. Okay. This has been found many years ago, and in fact, the people from the core machine learning communities has worked on this many years ago as well. Well, at the time, I had to say that people on the algorithm didn't know much about the hardware, so the effort was mainly on what we call now like non-structured sparsification. So the figure on the top is our initial hardware deployment. So the interesting situation, what we find is if we plug those algorithm-focused approaches and do the sparsifications on the deep neural networks, the purple curve on the top indicating across of the convolutional layers, the sparsification rate, always more than 80% and close to 100% in later layers, right? So roughly thinking, we expect 10 times of an improvement in performance. Well, many years ago when we started working in this field, we did it and tested on GPU, CPU, and many hardware platforms. Well, those bars indicating the exactly speed up. Interesting or surprising, what surprised us was, in fact, the speed up itself is very marginal, and for many layers, in fact, we suffer from the performance or the speed degradation instead of an improvement. So what exactly happens is non-structured sparsity kind of cause very poor data locality. And we know that the poor data localities, when we spread those data on the memories, we either consume the same size of the memory, or we have to go through some compression structures. And the encode and decode of those compressions, in fact, cause more latencies to execute. And that's the true reason, like, non-structured sparsity didn't work well as expected. Well, similar situations actually can observe from CPU executions. So here we demonstrate two examples. The orange curve shows the result of the structured sparsifications, and the blue curve then shows the results for the non-structured sparsification. Okay, so here when I'm talking about the non-structures, meaning it's purely came from the algorithm approach without considering the data structure. And the structure prunings, and what we tend to do over here is trying to remove the entire rows or the columns data. Okay. So when we're doing this, and obviously on the CPU executions, clearly the structure sparsifications and have lower sparsification ratios, but the performance is much better than the counterpart. And then it's generate another questions, and generally speaking, and what is the structure sparse in deep neural network, and how can we achieve this? Well, our concept was very, very simple. In fact, if you're thinking about the matrix operations, and this kind of illustrate a matrix, so any weights and connections can be removed group by group. And here, the definition of the group is also very flexible. It could be a rectangle block, it could be an entire row or entire column. It could even indicating the entire matrix. Okay, so a lot of times I'd say this can be defined by the users like you. Okay, because you know your model and you know your data, your application much better than the others. So we start with the convolutional neural network. And when looking at convolutional neural networks, okay, without talking about applications, simply a group could be channel, could be a 3D filter, 2D filter, it could be filter shape, it can even be entire layer. When we're talking about the layers, ResNet is a good example. It's essentially skip some layers, but it still having good performance, right? So based on this assumption, if you already define groups according to your situations, then the next step, in fact, is quite simple. Algorithm-wise, apply group lasso regularization to obtain this and benefits. What we do, once you have the group as indicating by the step 1, we apply group lasso on each group, and then we accumulate sum them up, and the sum term is used as the regularization term. Okay, so at the bottom here, as you can see, when we apply SGD, stochastic gradient descent optimizations, right? Usually we have a one term. This is the last term, right? And with the regularizers, we can plug in. So together, the last term helps to improve the accuracy of the model, while the regularization terms is trying to guide the pruning processes and ensuring, the weights is pruning by groups. Okay, so this is our methodologies, and we call this as structured sparsity learning, SSL. So I mentioned we actually started this in thread work many years ago, since in 2016. We start with a smaller network like LeNet. So the illustration over here is to show that because the network is so small, so we can clearly see that we can remove the entire 3D filters or the entire channels. Okay. Well, in fact, the middle figure here shows the results for the AlexNet at the time. Orange curve, again, indicating non-structure, and the green ones then corresponding to the structure versions. So the curve always indicating that structures have a lower sparsification ratios, meaning we have more weights maintained in the model. Well, the bars shows the truly measured the execution speed, and it's always show that the structures have a better execution speed than the non-structural ones. So later on, in fact, we extend the methodologies to many other models, including low short-term memory LSTM models, transformers, and a lot of more. Okay, and right now this methodologies has been kind of adopted by many companies as well. So this is the first part, talking about the software and hardware co-design for the efficiency. So the key information here is if we're able to take an abstract from a hardware side and plug into the DNN trainings, even this isn't just the simple indicators, it helps the deployment on the hardware side. Well, my second example is talking about our work called HiPEAC. So essentially the assumption here is right now many companies and research groups in developing the hardware with many accelerators. Okay, so the question then is, when we executing those DNN models on a group of accelerators, what is the best configurations? Is there anything we can do for the given software and hardware, whether certain configurations can help improve the performance or the efficiency? And particularly this work shoot for the deep learning training with multiple accelerator designs. One of the reasons is training itself consumes huge power and have a higher requirement on the hardware. So here we're looking at the tensors, and tensor here indicating the basic data unit in the deep training. And in the training procedures, we highly abstracted into 3 stages. The first stage is the forward path. Essentially, if you're looking at one layer L, the forward path have an input of the input feature map, multiplied by the weight matrices and produce the output feature map. Okay, and on the backward training path, we have the error matrix and the backpropagate multiply with the transpose of the weight matrices, and then produce the error matrix for the previous layer. And of course, the gradient is calculated based on the feature map and also the error matrices. Okay, so here, in order to understand the data requirement, we denote the tensor with the same shape by one symbol, like ABC indicate over here. Okay, so particularly for this, we ignore the activations and normalizations because based on the hardware test, the matrix operation consumes the most power. And right now we're talking about accelerator designs, which also primarily target by the layers. So, when we're talking about the large DNN executions, and we essentially talking about the how to partition the matrix to different accelerators in order to achieve parallel computation. For example, if we wanted to partition 3 matrices in one matrix multiplication on 2 accelerators, like I illustrate over here, right? So originally, a row from matrix A multiplied by a column on matrix B, and then produce results a node on the matrix C. So when we do partition on 2 accelerators, what happens is it could kind of a cut in the middle A and a B, right? As illustrated, we have 2 separate operations, and then each of them produce a partial sum. And then at the end, we need to sum them up. Well, talking about this in partition, okay, what I introduced was corresponding to the type 2 over here. Essentially, it's corresponding to the forward path. It's rooted from the forward path, and we naturally separate A and B's according to the accelerator numbers. Okay. I mentioned previously there are 3 paths: forward, backward, and also gradient calculation. So in fact, it corresponds to 3 types of the partitions. Like type 1 here is based on the gradient calculations, and type 3 is according to the backward calculations. Okay, so what does it mean? That means, the use of the accelerators according to the data allocation represent a different pattern. Well, and how this pattern going to affect our hardware executions, right? Over this part, we evaluated both computation cost and also communication cost. So computation cost itself is defined by the number of the flops of the multiplication of the 2 matrices. And over here, Ci represent the computation powers, right? So for the given situations, and if the hardware configuration is fixed, the computation cost itself and doesn't demonstrate tremendous difference. However, here we're talking about the data allocations and partitions. Its communication cost and could be very different. So here, the communication cost is defined by the size of the tensor divided by the effective network bandwidth of accelerator. And then we use this information sense to model the execution speed and so on and so forth. So when we're talking about this, again, it's partitioned into 2 parts. One is the intra-layer cost. For example, the previous slide talking about partial results, and we have to sum them up. That occurs within the same layer. It's also related to the interlayer communication cost, meaning when we have an accelerator is executed from a layer and pass the data to another layers, and how much cost that will be involved. Okay, so particularly talking about interlayer cost, and here is the illustrations. The illustration shows on layer L, it takes in type 2 partition, and layer L+1 also take layer 2 partition. Okay, so what happens, or the interesting part is at the transition part from layer L to the layer L+1, on the forward path, as you can see, the green part, the output feature map F L+1, right? We have multiple accelerators, and each of them generate partial summations, and we need to add them up. Okay, and when we pass that to the layer L+1, okay, what happens is the same matrices, the produced matrices, need to be partitioned and distributed into different accelerators, and each accelerator only have a portion of this. Okay. And on the backward path, the situation is kind of correspondingly different. So on the backward, each accelerator for the layer L+1s generate a portion of the results, and then we need to concatenate them together, producing one arrow map, and then this arrow map will be duplicated and distributed across accelerators. Okay, so you see the forward path and the backward path, in fact, they have a different data patterns. And that's introduced a different intra-layer cost. Well, corresponding to the how can we partition those and accelerator or datas, and corresponding to the combinations of the layer L versus the following layers. In fact, it results in 9 intra-layer communication patterns, and I just put over here. In fact, we monitor and created methodologies and trying to find the best combinations. And during this process, we apply the dynamic programming approach to minimize the overall communication cost. Okay. And also in our works, and we're trying to extend the partitions and from 2 accelerators to many of them, of course, right? So when we are doing this, and we use the hierarchical partitions, and so we start with the first layers and consider all of them, and then we recursively partition onto 2 accelerator groups and so on and so forth until it's reached to each individual accelerator. So a lot of the technical details can be found on our paper. I just show like one quick results. On the left-hand side, comparison our methodologies and with others in terms of the normalized and throughputs. And of course, and things that we present over here, we do expect it that the result is better than the others. But the more interesting part is on the right-hand side. The right-hand side shows, for example, for AlexNet, how is the partition types configurations changes and from layers. So as you can see, the early layer, convolutional 1 to 5 and fully connect layer corresponding to the accelerator numbers. So early layer, actually we have a more type 1, while when we switch to the later layer, particular fully connect layers, and then type 2 and 3s are dominant, okay? And type 3 further boosts the performance and from our previous work as well, okay? So if you're interested, feel free to reach out to me and I can show you our papers and with more detail. But particularly the takeoff from this work is even, we haven't the given hardware platforms and given the DNNs, there's still certain ways that we can better organize the data flows in order to achieve a better performance. So my last part I wanted to talk, in fact, is the hardware-driven neural architecture search. Okay, I mentioned like DNN also has the similar research lines, and we're quite interested in each other's research. So ultimate goal, in fact, is people not have to design those deep neural networks by themselves. In fact, even not very long ago, the DNN designs still heavily rely on the human experts. So you can imagine people kind of do the parameter tunings and people trying to design the architectures, and all these efforts are very time-consuming and also error-prone. Okay? But beyond this, and I think the deeper worry is such kind of a human approach and can result in homogeneous designs. What we meant is the dimensions or the factors as human being can explore is limited. So if you're looking at the previous network designs, right, people majorly focusing on how many layers, how wide of those networks, and some structure change, for example, ResNet, results in tremendous performance improve, and people were very excited. But it occurs very rarely. So the network design itself, and in fact, is pretty arbitrary. How can we really explore this in design space and find out or discover the useful topologies, the useful structures, and for various applications? That's essentially is our interest. So automatic machine learning, auto ML work itself, and this research line has been initiated many years ago. And generally speaking, it covers in different angles. For example, hyperparameter optimization, neural architecture search, algorithm selections. Well, since our group's mainly working on the DNN models, so we are primarily interested in the neural architecture search. Okay. So we work with some companies like Meta, Facebook, Qualcomm on this neural architecture research studies, and of course, industry companies, and the primary focus is still performance improvement. So we do have a lot of research in trying to improve the accuracy for example, transformers or the language processing and so on and so forth. But today, I'd like to particularly focus on our efforts on the neural architecture search with the topology-aware optimization, because the focus is more like hardware efficiency. So in this work, we call topology-aware, as I mentioned. We particularly interested whether we can discover some new topologies and how to do this. Okay. So novel architecture blocks is our interest, and we would like to construct the final deep neural network architectures with those new blocks. So on the left-hand side is illustrate the overall structure of our designs. So here, we construct a direct acyclic graph and DAGs, and the mentor graph is composed with many DAGs. The process actually coming from the mentor graph, and then we sample some DAGs and compile some sampler neural networks. And during this processes, and we also obtain some like B illustrated here, the proxy data set, and train on the proxy data sets and estimate its accuracy or the other performance values. Determined by the access at stage B's, and we can update the weight of each edge. Okay, so edge over here indicating the connections and across of different nodes. Okay, so on this DAG, okay, it's constructed of some cell topologies, as I illustrate over here. Each cell topology is trying to represent a certain data represent the capabilities. So in other words, higher levels, it's leads us to kind of an topology blocks. For example, ResNet block or mobile net block, or even combination of the convolutional layers and pooling layers. Okay. Each node within this cell topologies and represent a certain operations. As I mentioned, it could be 3 by 3 convolution, it could be 11 by 11 convolution, or poolings or the other operations. Well, the edge indicating the direction of the tensor flows. Okay. So this is a general structure. And in fact, if you're really talking about the very higher levels and many people taking the similar structure, the approach here is in how can we aware some new topologies. Well, considering time, I just give a very simple explanation over here. So what we do, or our intuition is in some similar cell topologies and will results to very similar architecture performance. And we tend to correlate and discover how to build the correlations in between. So particularly in this work, we created a graph embedding. So the right-hand side of the figures and show the overall flow. It's a little bit small. Basically, we divided it into 3 stages. The first stage is called kernel guide encoder training. So on this stage, we're trying to understand the structures and their architecture relationships. And over here, we access their similarities and access the reconstruction loss. So this is the first step, kind of learning the representation capabilities. And with this, we move to the second step called the building estimators. The estimator is trying to develop the relations of the structure versus its true performance. And over here, we kind of construct the efficiency score at the bottom over there. Particularly here, we introduce in the regularizer again in here to represent the hardware cost. For example, in these examples, we use the computation cost and Mach numbers, okay? And then at the bottoms, we use the bootstrap optimization. It's essentially a sample from the mentor graph and build, samples and assessment, the performance and its indicator to the overall mentor graph and buildings. The figure on the left-hand side shows before and after applying the graph embedding kernels and its results. And obviously, after applying the graph embedding kernels, and the graph and cosine similarity increased dramatically, indicating we are able to represent the similarity and building the relations to its performance. So that was kind of an early work, and later on, and particularly consider our background on the hardware design. So we are interested how to kind of apply the methodologies to EDA designs. So one reason over here is existing works and majorly focusing on some like CV, computer vision works, language models, and when we doing the EDA machine learning methodologies, and we find that its neural network architecture is not so rigid, and the new structures is more welcome. Also, for the EDA designs, and there's no kind of a golden model of the machine learning solutions. And then if you're able to discover some new prototypes, and that'll be interesting. So the procedure over here I illustrated is very alike of the general approach. The major difference here is we construct and fully customize the search space and with a lot of more building blocks. And then in this particular implementations, and we're interested in the FPGA deployment as the hardware cost constraints. So quickly coming over here, as you can see, the neural architecture search, when we apply to the routing problems, and the methodology can outperform other methodologies tremendously. But the most important information I wanted to show you is the best architecture for the discovered by other methodologies. So here we only show the 3 layers, and the first part, first stage, and there are more computations. So that's indicating the representation capability is necessary and important. And the middle stage structures is trying to improve the throughput. And then the last stage is kind of a mixed convolution in order to increase the receptive field. So it's clear it demonstrates the functionalities and across the layers, but for each stage, as you can see, it's way different from the traditional topology we construct from the CNN or the other networks. Okay, so this actually conclude my, finish by the details of my talk. I partition my talk into 3 particular works. The first 2 works is talking about the efficient, the efficient implementations, and the first is talking about the efficient inference. Basically, we need a training and hardware-friendly method to achieve a better CNN or the other neural network methodologies. And the second, tensor partitioning, is primarily focusing on the parallel trainings. But over here, again, I was interested in the configurations for the given hardware and the softwares. Well, the last part, we're trying to kind of grow our research and promote it to automatic flows. So we tried a neural architecture search, and through the processes, we discover some new topologies. I guess in longer times, and this will be some interesting topics to explore. I mean, since I have quick minutes, and so I can show quickly about the technology roadmap of our lab. I came to this conference. I know many people have hardware and architecture background, and my talk is primarily focused on the algorithm side. In fact, through this map, I wanted to demonstrate my background, in fact, is more like a circuit and architecture, but through the studies, and we figure out the algorithm and hardware co-design is essentially very, very important, and we kind of grow in big structures on the neural architecture search and machine learning acceleration. And in fact, on the right-hand side is more application domains, is to show how can we apply those techniques to the applications, hardware system demonstration and the development. Welcome to discuss more. So I guess, and this is the end of my talk. Thank you.